Welcome to our deep dive into the fascinating world of machine learning. In this video, we'll unravel the mysteries behind how machine learning algorithms actually work. Whether you're a curious beginner or someone looking to brush up on the basics, you're in the right place. Machine learning is all about teaching computers to learn from data, recognize patterns, and make decisions with minimal human intervention. But how does this process really unfold? Let's start by understanding what machine learning is and why it's become such a crucial part of modern technology. From voice assistants to recommendation systems, machine learning powers many tools we use daily. Let's embark on this journey together and see how it all comes together. At its core, machine learning is a subset of artificial intelligence that enables computers to learn from experience. Instead of being explicitly programmed for every task, these systems use data to identify patterns and improve over time. Imagine teaching a child to recognize animals by showing them pictures. Machine learning works in a similar way. The more examples the algorithm sees, the better it becomes at making predictions or decisions. This ability to adapt and improve is what sets machine learning apart from traditional programming. Now, let's explore the main types of machine learning and how they differ. Supervised learning is one of the most common types of machine learning. In this approach, algorithms are trained using labeled data, which means each example in the dataset comes with the correct answer. Think of it like a teacher guiding a student with the right solutions. The algorithm learns by comparing its predictions to the actual answers and adjusting itself to minimize errors. This method is widely used for tasks like image recognition, spam detection, and predicting house prices. Supervised learning is powerful because it leverages known outcomes to improve accuracy over time. Unsupervised learning takes a different approach. Here, algorithms work with data that doesn't have labeled answers. Instead, the system tries to find patterns, groupings, or structures within the data on its own. It's like exploring a new city without a map, discovering neighborhoods and landmarks as you go. Common applications include customer segmentation, anomaly detection, and market basket analysis. Unsupervised learning is especially useful when you have lots of data but no clear outcomes to guide the learning process. Reinforcement learning is inspired by how humans and animals learn through trial and error. In this approach, algorithms interact with an environment and receive feedback in the form of rewards or penalties. The goal is to maximize the total reward over time by learning which actions lead to the best outcomes. This type of learning is used in robotics, game playing, and autonomous vehicles. Reinforcement learning is unique because it focuses on learning a sequence of decisions, adapting strategies based on ongoing feedback. Every machine learning algorithm is built from a few essential components. These include the data, the model, the learning process, and the evaluation method. The data provides the foundation, the model represents the mathematical structure, the learning process adjusts the model based on data, and evaluation checks how well the model performs. Understanding these building blocks is crucial for grasping how algorithms work and why they succeed or fail in different scenarios. Data is the lifeblood of machine learning. Without quality data, even the most advanced algorithms can't perform well. Data comes in many forms: numbers, text, images, and more. The process starts by collecting and preparing this data, ensuring it's clean and relevant. The better the data, the more accurate and reliable the algorithm's predictions will be. This is why data scientists spend so much time on data preparation before any learning begins. Choosing the right model is a critical step in machine learning. Different models are suited for different types of problems. For example, linear regression works well for predicting continuous values, while decision trees are great for classification tasks. The choice depends on the nature of your data and the problem you're trying to solve. Selecting the right model can make a huge difference in the performance and accuracy of your algorithm. Training is where the magic happens. During this phase, the algorithm processes the data and adjusts its internal parameters to minimize errors. It's like practicing a skill over and over until you get it right. The algorithm uses mathematical techniques to find the best fit for the data, learning from mistakes and improving with each iteration. This process continues until the model reaches an acceptable level of accuracy. Once the algorithm is trained, it's time to test its performance. This involves using a separate set of data that the model hasn't seen before. By comparing the model's predictions to the actual outcomes, we can measure how well it generalizes to new situations. Evaluation metrics like accuracy, precision, and recall help us understand the strengths and weaknesses of the model. This step is crucial for ensuring the algorithm works reliably in the real world. Machine learning is rarely a one-and-done process. After evaluating the model, data scientists often go back and tweak the algorithm, adjust parameters, or even collect more data. This iterative cycle of training, testing, and refining helps create models that are robust and reliable. The goal is continuous improvement, ensuring the algorithm adapts to new data and changing conditions over time. Feature engineering is the art of selecting and transforming the right data attributes to improve model performance. Not all data points are equally useful. Some features have a bigger impact on predictions than others. By creating new features or modifying existing ones, data scientists can help algorithms learn more effectively. This step often requires creativity and domain knowledge, making it a key part of the machine learning workflow. Two common challenges in machine learning are overfitting and underfitting. Overfitting happens when a model learns the training data too well, capturing noise instead of the underlying pattern. Underfitting occurs when the model is too simple and fails to capture important trends. Balancing these issues is crucial for building models that perform well on new, unseen data. Techniques like cross-validation and regularization help address these challenges. Cross-validation is a powerful method for evaluating machine learning models. It involves splitting the data into multiple parts, training the model on some parts, and testing it on others. This process is repeated several times to ensure the model's performance is consistent and not just a fluke. Cross-validation helps prevent overfitting and gives a more accurate picture of how the model will perform in the real world. Regularization is a technique used to prevent overfitting by adding a penalty for complexity to the model's learning process. By discouraging overly complex models, regularization helps ensure the algorithm focuses on the most important patterns in the data. Common methods include lasso and ridge regression, which add different types of penalties to the model's parameters. Regularization is a key tool for building models that generalize well. Hyperparameters are settings that control how a machine learning algorithm learns. Unlike model parameters, which are learned from data, hyperparameters are set before training begins. Examples include learning rate, number of layers, and tree depth. Tuning these values can have a big impact on model performance. Data scientists use techniques like grid search and random search to find the optimal hyperparameter setting. Gradient descent is a fundamental optimization algorithm used in many machine learning models. It works by iteratively adjusting the model's parameters to minimize the error between predictions and actual outcomes. Imagine rolling a ball down a hill to find the lowest point. That's the essence of gradient descent. This method is efficient and widely used for training neural networks and other complex models. Loss functions are mathematical formulas that measure how well a model's predictions match the actual outcomes. The goal of training is to minimize this loss, making the model as accurate as possible. Different tasks use different loss functions, for example, mean squared error for regression and cross-entropy for classification. Choosing the right loss function is essential for guiding the learning process in the right direction. Activation functions are key components in neural networks. They determine whether a neuron should be activated or not, introducing nonlinearity into the model. Common activation functions include ReLU, sigmoid, and tan. These functions help neural networks learn complex patterns and make decisions that go beyond simple linear relationships. Without activation functions, neural networks would be limited in what they can achieve. Neural networks are inspired by the human brain and consist of layers of interconnected nodes, or neurons. Each neuron processes input data and passes the result to the next layer. By stacking multiple layers, neural networks can learn to recognize highly complex patterns. They are the backbone of many modern machine learning applications, including image recognition, natural language processing, and more. Decision trees are intuitive models that split data into branches based on feature values. Each branch represents a decision rule, leading to a final outcome at the leaves. Decision trees are easy to interpret and visualize, making them popular for classification and regression tasks. However, they can be prone to overfitting if not properly managed. Random forests are ensembles of decision trees. By combining the predictions of multiple trees, random forests reduce the risk of overfitting and improve accuracy. Each tree is trained on a random subset of the data, and the final prediction is made by averaging or voting across all trees. This approach is widely used for both classification and regression problems. Support vector machines, or SVMs, are powerful algorithms for classification tasks. They work by finding the optimal boundary that separates different classes in the data. SVMs can handle both linear and nonlinear problems by using kernel functions. They are especially effective in high-dimensional spaces and are used in applications like text classification and image recognition. K-nearest neighbors, or KNN, is a simple yet effective algorithm. It classifies new data points based on the majority class among its nearest neighbors in the training set. KNN doesn't require a training phase, making it easy to implement. However, it can be slow with large datasets and is sensitive to the choice of distance metric. Clustering algorithms group similar data points together without using labeled data. The most popular method is k-means clustering, which partitions data into k-clusters based on similarity. Clustering is widely used for customer segmentation, image compression, and organizing large datasets. It helps uncover hidden structures and relationships within the data. Dimensionality reduction techniques simplify data by reducing the number of features while preserving important information. Principal component analysis (PCA) is a common method that transforms data into a smaller set of uncorrelated variables. This makes models faster and less prone to overfitting, especially when dealing with high-dimensional data. Ensemble methods combine multiple models to improve overall performance. Techniques like bagging, boosting, and stacking leverage the strengths of different algorithms. By aggregating predictions, ensemble methods often achieve higher accuracy and robustness than individual models. They are widely used in competitions and real-world applications. Bias and variance are two key sources of error in machine learning models. High bias means the model is too simple and misses important patterns, while high variance means the model is too sensitive to noise in the data. The goal is to find the right balance, known as the bias-variance trade-off, to build models that generalize well. For feeding data into a machine learning algorithm, it's essential to preprocess it. This includes cleaning missing values, normalizing scales, encoding categorical variables, and splitting data into training and testing sets. Proper preprocessing ensures the algorithm receives high-quality input, leading to better performance and more reliable results. Missing data is a common challenge in real-world datasets. Algorithms can't learn effectively if important information is missing. Techniques like imputation, where missing values are filled in, or removing incomplete records, help address this issue. Choosing the right strategy depends on the amount and nature of the missing data. Scaling and normalization are important preprocessing steps. They adjust the range of data features so that no single feature dominates the learning process. Common methods include min-max scaling and standardization. Proper scaling helps algorithms converge faster and improves overall model performance. Many datasets include categorical variables like colors or product types. Machine learning algorithms require numerical input, so these categories must be encoded. Techniques like one-hot encoding and label encoding transform categorical data into a format the algorithm can understand, ensuring all information is used effectively. To evaluate a model's performance, data is typically split into training, validation, and testing sets. The training set is used to teach the algorithm, the validation set helps tune parameters, and the testing set measures final performance. This separation ensures that the model is evaluated fairly and can generalize to new data. Different tasks require different evaluation metrics. For classification, common metrics include accuracy, precision, recall, and F1 score. For regression, metrics like mean squared error and R-squared are used. Choosing the right metric helps ensure the model meets the specific goals of the problem at hand. Confusion matrix is a tool for visualizing the performance of classification algorithms. It shows the number of correct and incorrect predictions for each class, helping identify where the model is making mistakes. By analyzing the confusion matrix, data scientists can fine-tune models and improve accuracy. ROC curve and AUC area under the curve are important tools for evaluating classification models. The ROC curve plots the true positive rate against the false positive rate at different thresholds. A higher AUC indicates better model performance. These tools help compare models and choose the best one for a given task. Once a model is trained and evaluated, it's ready for deployment. This means integrating the model into real-world applications such as mobile apps, websites, or business systems. Deployment requires careful planning to ensure the model runs efficiently and delivers accurate predictions in production environments. After deployment, models need ongoing monitoring and maintenance. Data can change over time, leading to a phenomenon called model drift. Regularly checking performance and updating the model ensures it continues to deliver accurate results. Maintenance is an essential part of the machine learning lifecycle. Machine learning algorithms can have significant impacts on society. It's important to consider ethical issues like bias, fairness, privacy, and transparency. Ensuring that algorithms are used responsibly and do not reinforce existing inequalities is a key challenge for data scientists and organizations alike. Machine learning is everywhere, from voice assistants and recommendation engines to fraud detection and medical diagnosis. Its ability to analyze vast amounts of data and make accurate predictions has transformed industries and improved countless aspects of daily life. The possibilities are nearly endless, and new applications are emerging all the time. Despite its power, machine learning has limitations. Algorithms can struggle with biased or incomplete data, lack of interpretability, and high computational costs. Understanding these challenges helps set realistic expectations and guides the development of better models and solutions. The future of machine learning is bright and full of potential. Advances in deep learning, reinforcement learning, and quantum computing promise to unlock new capabilities. As technology evolves, machine learning will continue to shape the way we live, work, and interact with the world around us. If you're interested in exploring machine learning further, there are many resources available. Online courses, tutorials, and open-source libraries make it easier than ever to get started. Building simple projects and experimenting with real data is a great way to learn and gain practical experience. We've covered a lot of ground in this video, from the basics of machine learning to the inner workings of algorithms and their real-world applications. Remember, machine learning is about teaching computers to learn from data and make better decisions. With the right data, models, and techniques, the possibilities are endless. Keep exploring and stay curious. Thank you for joining us on this journey through the world of machine learning algorithms. We hope you now have a clearer understanding of how these powerful tools work and why they matter. Stay tuned for more insightful content on technology and innovation. Until next time, keep learning and exploring new horizons.